In this video lecture, we'll look at another type of graphical model used in Bayesian machine learning, known as hidden Markov models. These models are particularly useful for dynamic systems and dynamic processes. In the first part of the lecture, we'll look at the concepts and characteristics of hidden Markov models, and then in the second part, we'll look at a specific type of inference used in HMMs, known as filtering. So as we said, hidden Markov models are useful for dynamic systems or time series modeling and problems in that area. And they can include things like healthcare, where we're looking at, for instance, patient information as it comes out of an ICU. It can also be used in areas in bioinformatics, ecology, natural language processing, where we're looking at text or speech over time, and lots of other areas where there's this dynamic nature to a process. And the way that we build the model, and the hidden Markov model, is with two sets of discrete or possibly continuous, in the case of the visible variables, nodes. And as I say, we've made them into this bipartite division between the two types of nodes, very much like what we saw in the Boltzmann machine, or the restricted Boltzmann machine, where we had hidden units and visible units. We have the same thing in a hidden Markov model. We have visible nodes in the graph, represented here by v of t, and then we have hidden or latent variables represented by h sub t. And notice that the hidden units can be connected to each other, and actually they're only connected to their neighbors. So as we show, h of t minus 1 is connected to h of t, which is then connected to h of t plus 1, which is then connected to h of t plus 2, and so forth. Where the visible units are not connected to each other, they are, however, connected to the hidden units. And notice also that we've returned to our Bayesian network in that we have directed arcs, not undirected arcs as we did with the Boltzmann machines and with Markov random fields. So the property that we use here is, again, a Markov property, and we use it particularly for these hidden or latent variables. That's where the Markov property has its real application. The observed or visible variables are dependent on these hidden variables, and they're dependent, as we saw in our Bayesian networks, through these conditional probabilities. In this case, it's the probability that v of t takes on a certain value given h of t, or the visible variable at t takes on a value given the hidden variable at t. And this defines, as we saw again in Bayesian networks, a joint distribution, which is the product of all these conditional probabilities. And we can represent that here. And because we have this Markov property, we note that these hidden units only depend upon the unit that occurred before them. So in other words, h of t, the value of it only depends upon the value of h of t minus 1, and none of the other h of t's that may have preceded it. For a stationary hidden Markov model, the transition and observation distributions are constant through time. And we denote these as, again, the probability of h of t that takes on a particular value given the hidden state h of t minus 1 that occurred before it, and the probability of a visible variable t given that hidden unit at time t. Those are constant over time. So let's look a little bit more closely at this transition distribution, and in particular we're going to put it into a matrix as we do in most Markov processes or Markov chains. So the transition distribution that we're interested in then is the transition from h of t, hidden state at time t, to hidden state at time t plus 1, h of t plus 1. And we can use that to define a matrix then, which is h by h, capital H by h, where capital H is the number of states for the hidden units. And we're going to let aij then be defined to be this matrix, okay? So the components of the matrix A are going to be aij, where j is the state at which hidden unit at time t is in, and I is the state at which hidden unit at time t plus 1 is in. And again, these states come from 1 through h, the number of states in the hidden units. And we have an initial distribution that we define as a sub I, which is simply going to be the probability that at unit 1, hidden unit 1, it's in one of those h states. So let's now look at the observation distribution. And the observation distribution has elements such as P of V sub t given H of sub t. And V sub t, again, is the state of the visible unit at time t, and H sub t is the state of the hidden unit at time t. And just as we could for the transition distribution, we can put the observation distribution into a matrix. In this case, we have the discrete states 1 through V. These are the states for the visible units. And for the observation matrix, we again have states 1 through H, as we saw before, for the hidden units. So we have a matrix then that is V by H. And we'll represent that matrix with notation B, where Bij is the ijth element of the matrix, and that represents the probability that the visible state at time t is in state I, and the hidden unit at state t is in state j. And I, of course, can take on one of the visible unit values, state values from 1 to v, and j can take on one of the hidden state values from 1 to h. We could have continuous outputs instead of discrete outputs. So in other words, at hidden state j, we could have a discrete output, and that discrete output then would be represented as a selection from a possible distribution or a density function, which would be represented by P V sub t for the output of that visible unit at time t being drawn from a continuous density function instead of being a discrete state. Again, the hidden units, however, are discrete, and they're in 1 through h states. All right, let's now look at a particular kind of inference in HMMs known as filtering. And in filtering, we are inferring the present. We're carrying out a sequence of what are called message passing up and down up the chain, and the passing is actually up and to the right, as we'll see. And our goal is to infer what the current state is. So what we want to know is, where are we at time t in terms of this hidden state? So we want to infer a hidden state h sub t given all the previous states, and that states 1 through t that we can observe. So these are the visible states 1 through t. So what we want is we want to find this probability of h sub t given all the previous visible states 1 through t, where t is the present time. It's where we're at currently. So let's see how this works, and we're going to get at it, not surprisingly, using Bayes' rule. And this is a very straightforward notion. We're going to take this conditional probability of the hidden state at time t given all the visible states 1 through t. And we're going to represent it first as this joint distribution between the hidden state at t and the visible states through time t. And then we're going to look at that joint distribution, and we're going to do what we've done over and over in the course. We're going to use conditioning. And in this case, we're going to condition on the previous hidden state. So we want to know where we are at hidden state at time t in the hidden unit. And we're going to do that by going back one state and saying, okay, where were we in the previous unit? And then we're going to look at all those probabilities, and that's our conditioning. So we're going to sum over all those probabilities for those hidden states at one time step back. Notice we've also broken out the visible units. We've said we've got visible units 1 through t, but we've just pulled out the last one to make it special here in terms of how we're going to do the next notation. So the way we're going to do this is we're now going to go through, we're going to write these conditional probabilities. And here's where we've pulled out that v sub t. So this is the visible state at time t. And then it's conditioned on all these other things. The visible states at 1 through t minus 1, the hidden state at time t, and the hidden state at time t minus 1, all the other elements that we saw above. But we note that the visible state at time t is independent of all the other visible states, so we can immediately eliminate those terms. It's also independent of the previous hidden state because it only depends upon the current state. So it's independent of all previous hidden states given the current state. And that's what that graph model does. So that first probability then is just going to reduce to the probability of v sub t given h sub t. The second conditional probability we have a similar kind of logic at work here. We've got the hidden state at time t. We've got the dependence now on visible states 1 through t minus 1 and hidden state t minus 1. But note that the hidden state at time t does not depend at all on the visible states. So we can remove those. So it's only h of t given h of t minus 1. And finally, we have the conditioning that we're doing, which is on states h of t minus 1. That's what we're summing over all of those. And then we've got the conditional element that was in the original conditioning, which is v of the visible states from 1 to t minus 1. So when we remove all those states that don't play a role in this equation, we're left with this equation where, again, summing over all the values for the hidden node or the hidden unit at time t minus 1. And we're doing that by multiplying starting with the probability of the visible unit at time t given the hidden unit at time t times the probability of the state of the hidden unit at time t given the hidden unit at time t minus 1. And that in turn times the probability of the hidden unit at time t minus 1 times the states of the visible units from 1 through t minus 1. And we can in turn rewrite that by removing that first element because that doesn't have an h of t minus 1 in it, so we can pull it in front of the summation. And we'll call all of that equation 1. And we'll use it in the next development here, which is the filtering recursion. And this is called an alpha recursion. So we're going to define alpha h of t just to be this joint probability, the probability of the state of the hidden unit at time t and all the visible units from time 1 through time t, 1 to the current time. Then from that equation 1, which we just developed, we can define this alpha recursion as follows. So alpha of the hidden state at time t then, that we've defined, it's just a way of writing that joint probability, but we're going to call it alpha of h of t. That's going to be equal to two major components. One component is, we could call it a corrector component. It's giving us what the value is of the visible unit given the hidden unit at the current time. And that's all times that summation. Then we'll call that the predictor unit. So all we're doing is we're just rewriting equation 1 now in terms of alpha h of t. That's all we've done here. And this equation is good for t greater than 1. And for t equal to 1, the alpha h of t is simply equal to that joint distribution h of 1, v of 1, both of those at the first time unit. And we can rewrite that in terms of conditional probabilities as the conditional probability of the visible unit at time 1 given the hidden unit at time 1 times the probability of the state of the hidden unit at time 1. Okay, we're now going to use Bayes' rule here to give us this filtered posterior distribution, which is what we want. This is what we're looking for in filtering, the probability of h of t given all the visible states that we've observed between 1 and time t. So we want to give a good estimate for where we might be in this process in terms of the hidden unit given everything that we've observed through those visible units. And that, by Bayes' rule, is just proportional to that alpha h of t. It's proportional to that joint probability that we saw, h of t and v of 1 to t. The likelihood, which is the normalizing, gives us the normalizing constant we can find from the sum rule. And that's simply taking and conditioning now. And what we're doing is we're conditioning on the hidden unit at time t. So we're summing over all the possible values for the hidden unit at time t in order to find this likelihood of the visible units 1 through t. And we can rewrite that because we've defined what's that summation, that joint probability in the summation is just alpha h of t. So that's the normalizing constant. We're just going to sum over all those alpha h of t's, and that gives us the normalizing constant to turn those h of t's into probabilities. Well, let's look at an example of how we can use this, and this is kind of a fun little example. Imagine that Sally's burglar alarm has gone off in her home, and she lives, or in her apartment. She lives in an apartment with 3 rooms, and is sure that the burglar is entered through room 1. That's the only way the burglar could get in. She has motion sensors in each room, and they've gone off in the last 3 hours in rooms 1, 3, and 3. and they have the following observational probabilities. So what this is telling us then is this is giving us the probability that given that we are in room 1, what is the likelihood that sensor 1 has gone off, probability that we're in room 2, the likelihood that sensor 2 has gone off, and so forth. And you can see that if we're in room 1, the probability that the sensor has gone off, the sensor 1 has gone off for room 1 is 0.6. And if we're in room 1, the probability that the sensor in room 2 has gone off is 0.2. And in a similar fashion, if we're in room 1, the probability that the sensor in room 3 has gone off is 0.2. And you can see that this gives us the observational matrix for this particular problem. The transition matrix, and this is in hours, so we're just going to define our transition between these hidden states. So these give us the probability of going from room to room. And this is the probability that if the burglar is in room 1, that they will stay in room 1 is 0.1. And the probability that if they're in room 1, they'll go to room 2 is 0.4. And finally, if they're in room 1, they'll go to room 3 with probability 0.5. So you can work out and see what the rest of these probabilities are. And this gives us the transition matrix in hours between rooms for this particular problem. So now the question is, it's 3 hours since the first alarm went off. Where is the burglar? So we want to know where the burglar is at hour 3. Okay, we can easily solve this using that filtering, and here's the solution to it. We won't go through the details. I'll let you work out these individual details, but you should be able to satisfy yourself that alpha 1 is 0.6 and all the other ones are 0. Because remember that this is the probability, this is this joint probability that at time 1, the burglar is in room 1 and the alarm has gone off in room 1. And we know from Sally, and that happens to be 0.6 when we look at the probability that the alarm goes off, given that the burglar is in room 1, is 0.6 by our observation matrix. On the other hand, they are in room 1 with certainty. Sally knows for certain that the burglar at hour 1 has to have come in through room 1. That means that the probability of coming in through those other rooms is 0, which is what's zeroing out those other terms in that alpha vector. Now, once we have alpha 1, we can easily calculate the probability of hidden state 1 given the observations at time 1, because that's just looking at that alpha vector, 0.600, and normalizing it. So we take 0.6 and divide it by the sum of 0.6 plus 0, which is 0.6, which gives us 1 in the first element. And the zeros in the other elements follow logically. So go ahead and work this filtering problem out, and what you're seeing here is the solution to it, and see if you get this solution to the filtering problem. And in the next class, we'll talk about the 3 other types of inference that we can do in HMM. And these will illustrate the other interesting types of problems we can solve with hidden Markov models.